Okay.
So this is Data670, and so this is the data analytics practicum. And part of it is we're adding this new presentation to show other students what 670 is about, as well as other students in 670 to see what everybody's working on. And so this is our first time doing this in July 10th, 2017. And so Bahana Smith is going to start reviewing his project and what he's doing. So if you can transfer to him.
Hello, this is Bohannon. Can you hear me?
Yes.
Yes.
I can hear you.
Hey, hello. My name is Bohannon Smith, and I'm doing I'm on a data understanding part of my NASA project. What I'm doing is putting together an analysis of landslide fatality across the globe, and I will be using Watson Analytics for it. In my assignment, I will be using Watson Analytics to present the results, and also use descriptive statistics in the displays, in the dashboards, and the expert storybook as we learned in the last semester. I'll be using, I will create a dash.
You may want to, you have to go to share your screen if you want us to see your slides.
Oh,
see
okay.
at the top where it says share, and this is for everybody. See that? Do you have the menu that says share up top?
Okay, so I'm looking for a menu that says share.
Right at the top of the Cisco Meeting Center.
Okay. 1 second.
If you see share.
I see it. I just clicked it.
Share my, and then the pull down, click on my screen. Now we're seeing your slides, buddy.
Okay, so now you can, okay, now you're seeing my slides. Okay, so this is the NASA Landslide Data Analytics Data Analysis Project. So I think everybody's the lead of, their own team, and I've been contracted to NASA, and I'm assisting them with this assignment based on a project that is designed to address landslide fatality data. So I'm comparing the United States fatality rate across the globe. And what interests me most about it is that the United States has a high fatality rate compared to that of several third world countries. However, more developed European countries such as like Italy and France and Germany and Switzerland and Sweden, they're not really on the list, but the United States for some reason has a high fatality rate just like India and China. So I got this data from NASA. I collected it from the earthdata.com from NASA, and it's been very helpful. NASA has given me a lot of angles to base it on, and this project will be used to mark how the U.S. compares to other countries in terms of landslide fatalities. I will be using 6 points in this project, such as the causes of the landslide in terms of the relation of variables such as the types of landslide, whether they're mudslides, whether they're snow avalanches, the amount of precipitation that is involved in each country, in each geographical area, and things like that. So as of right now, do I have any questions from anyone? Are you guys still with me?
Now, where did you get the idea to do this project?
So at the beginning of the semester, we were told that, NASA and AIR, were going to be some projects. So my undergrad was BS in psychology, so I was just going to do some social science stuff, same old thing, kind of cookie cut, my way through it. However, just, when you guys were talking about NASA at the beginning of the semester, it kind of brightened my idea about let's do something different, something that's not in my comfort zone. So I started looking at the NASA data and everything, and I saw the landslide fatality. So I figured that this is something new. This is something new that I can get into that shows me a different way of looking at data, something fresh, and something that I can, be interested in. Any other questions?
How big is the data set? Do you know?
It has about 10,000. It has about 10,000 points, and the variables. I can bring it up right here.
Okay.
Landslide catalog. I think that's it right there. Okay. That's not it. Landslide. Go to export. So how about I just bring up the data? I can bring it up on Excel.
Yeah, that'd be great.
So here's the Excel. So as you can see here, we have many variables, but it is a very, very large data set. And I had to go through and, put some zeros in the parts because a lot of places, as you can see here, that had zero fatalities, a lot of those spaces were blank. And since those spaces were blank, I had to go in and fill the zero in for that. And one of the points that I addressed in my analysis was that since a lot of countries had zero fatalities and some fatalities were so high that in further analysis, I may take out the zeros altogether. This study on NASA, this landslide data highlights the important physical connection between rainfall, hydrological processes, and slope stability, and provides a useful prototype model. So these graphs here comes from the Earth data from NASA that I use, and it just shows how the different countries relate to each other and the range of fatality. Do I have any other questions?
By the way, if others want to ask questions, I've got most of you on mute, so you'd have to either put something in the chat room where I can unmute you or raise your hand with the little icon for hand raising. But I can unmute you if you have a question. Who's next, John? Do you have I forgot what the agenda was.
David George is next.
All right, let me see if I can get David, the ball down to David. David, like Bohannon, you'll have to go up to the share icon at the top of the screen and share your screen. I guess I should unmute David. Where is he? He's unmuted.
Can everybody see my screen?
Yes.
Okay, good. Okay, my name is David George, and I'm pleased to be given the opportunity to make this presentation. Cervical cancer is easily treated if detected and treated early. There are some patient populations in the world that do not receive proper screening because of limited healthcare resources. In other areas, resources are sufficient, but cost of healthcare is a concern. The more efficient allocation of resources is sought to improve overall outcomes while reducing costs. This analysis will be performed for the benefit of the healthcare industry to gain insight of risk factors related to cervical cancer and to develop a model that can be used to identify individuals that are a higher risk of developing cervical cancer. As stated by the Centers for Disease Control, cervical cancer used to be the leading cause of cancer death for women in the United States. Fortunately, the number of cases of cervical cancer and the number of deaths from cervical cancer have decreased significantly in the past 40 years. The CDC notes that cervical cancer is the easiest gynecological cancer to treat if detected and treated early. Therefore, finding indicators that would aid in identifying those at high risk would be beneficial in allocating healthcare resources towards a patient population that would benefit the most. This applies to areas where resources are limited, relatively limited, and where efforts need to be focused to maximize benefit. The value of this analysis can also be realized in areas where resources are not limited in an effort to improve outcomes and decrease costs. Healthcare is moving away from the broad application of preventive healthcare guidelines and towards customizing treatment based on the risk factors of individuals. The objective of this analysis of this data set is to present useful insights from the data provided and to construct a model to predict the likelihood of cervical cancer based on the values of certain identified attributes. This model should inform decisions with regard to allocating limited resources where this applies and in the formation of customized preventive treatment plans based upon individual patient risk. The data was collected at a university hospital in Caracas, Venezuela. The data set comprises demographic information, habits, and historic medical records. Some patients decided not to answer some of the questions because of privacy concerns, which resulted in missing values. The data set provides the following attribute information: age of the patient, number of sexual partners, age of first sexual intercourse, number of pregnancies, does the patient smoke? If so, how many packs per year? Does the patient use hormonal contraceptives? If so, for how many years? Does patient use an intrauterine device? If so, for how many years? At the time of the screening, does the patient have an STD? And if they do, how many? Attributes 14 through 25 are the data provided for specific STD diagnoses. Attribute 26 provides the total number of times the patient has been diagnosed with an STD, followed by the year since the first STD diagnosis and the year since the last STD diagnosis. Attributes 29 through 32 are a listing of diagnoses from the screening process. Attribute 29 is our target variable for if a patient was diagnosed with cervical cancer. The final four attributes are the diagnostic methods used in the screening process. I'm using R in my analysis. The data structure can be evaluated in R, and various visualization techniques employed to evaluate the data, gain insight, and determine what pre-processing steps should be taken. The data set contains missing values, so each attribute was analyzed individually for missing data. In 34 of the 36 attributes, the data was present in at least 86% of the patient records. Patients did not provide information significantly for two attributes: the years since first STD diagnosis and years since last STD diagnosis, where the data was missing in 92% of the records. These two attributes, since they are missing so much information, were removed from for the purpose of analysis. Once the data set is prepared for modeling, the data will be divided into a training set and test set. The training set will be used to build a decision tree model in R, and then check for accuracy and so on. Additionally, I'm going to build a logistic regression model and compare the results of the two. See how the results compare between the two. The analysis of this data set should help to identify the risk factors that are most likely to be linked to cervical cancer. This information can be used to direct research efforts to identify causal relationships. Additionally, this information can be used to educate the public on healthy habits that reduce risk for developing cervical cancer. This analysis will also be used for modeling that will facilitate greater efficiency in the allocation of healthcare resources in the treatment of cervical cancer. There is a recognized need to lower the cost of healthcare and improve outcomes in the United States. A one-size-fits-all approach is too costly and inefficient. Developing a predictive model will assist healthcare practitioners to fabricate customized preventive treatment plans based upon the needs of individuals. This will contribute to greater efficiency of care with better outcomes at lower costs. The American Cancer Society estimates there will be approximately 12,000 new cases of invasive cervical cancer diagnosed in the United States this year, and approximately 4,000 women will die from this affliction. Cancer Research Fund International states that cervical cancer is the fourth most common cancer in women, and approximately 84% of diagnosed cervical cancer cases occur in less developed countries. The American Cancer Society states that the 5-year survival rate of people with stage 0 and 1A is 90, and the 5-year survival rate drops to. Hello? Can you still hear me?
Yes.
Okay. The 5-year survival rate then drops to 63% for the next stage. So successful treatment of cervical cancer is critically dependent on early detection. Early detection is more difficult to achieve in locations where healthcare resources are limited. The largest percentage of cervical cancer diagnoses are found in lesser developed countries where the ability to effectively screen for cervical cancer is constrained by limited means. The development of a predictive model should prove useful in targeting healthcare resources to patients that are at higher risk. Furthermore, this model should prove useful in the customization of healthcare in areas where improving healthcare outcomes while lowering treatment costs is the focus. So with that, I thank you for your attention, and I'm happy to answer any questions.
What time frame is the data from?
Hold on. Now, I don't have the data set with me, and I can't remember off the top of my head. I can get that information to you, though.
No
It's fairly recent. It was in the past couple of years. I don't remember exactly, though.
Okay. And where did you find the data?
From
where was it available?
The California Dataset. My original plan was to try to actually use healthcare data that I have in my current employment, but I couldn't get permission to use that information because of protected information. So I tried to do something similar. So I just looked at data sets that were healthcare related.
And is there much move to genomic sequencing to determine the course of treatment? Did you read? I'm assuming you did some reading to determine the next step.
Right. That depends a lot on the disease or anomaly that you're trying to address. It's very expensive and very labor intensive. Eventually, I'm sure there will be a lot of tests and so on, but that can't be universally applied, at least at this juncture. And something like this, probably with the data that we have, we don't need genomic testing to be able to provide insight and useful models to address this particular issue.
Do others have questions for David?
I have a question. Is the statistics that you were talking about, the 84% of patients and what have you, did you get that through your R analysis, or is that information that you got through research? And
research. That was from research. That was actually information provided by Cancer Research Fund International. It's a global organization.
Thank you so much.
Okay.
Who's next, John? You remember?
Greg Smith is up next.
Greg Smith. Let me drag the presenter ball down to Greg. All right, Greg, you should be able to go up to the share menu and share your screen.
Okay, do you have my screen now?
Yes, we do.
Great. So I'm Greg Smith, and I'm happy to be presenting my Data670 capstone project, predicting late career pitcher success from PitchFX data, which is ongoing research under the guidance of our professor, Dr. John McKeeby. The objective of this project was to build a predictive model that will reduce the amount of risk associated with signing late career starting pitchers. Starting pitchers are the most in demand and highest paid position in Major League Baseball, with an average annual salary this season of $5.8 million. The figure on the right shows the distribution of pitchers by the length of career in years. And so as you can see, there's not a lot of job stability in pitching in the major leagues. A lot of guys never even get beyond the first year. And then attrition continues beyond that. But each team needs to have 5 starting pitchers in their rotation. And there simply aren't really enough good pitchers to go around. So they can usually manage to fill the first 3 positions with established pitchers who are in their prime, somewhere between 3 and 10 years of major league service. But finding someone to fill those last 2 positions in the rotation can be really hard. And so that leaves them with something of a challenge in that, do they want to take a chance with a rookie pitcher who are inexpensive, but they fail at a 75% rate? Or do you take a chance with a veteran who's late into his career and hope that he has one more good season left? The primary data set used for this project is Major League Baseball's PitchFX. The league has a system of high-speed stereoscopic cameras that are installed in every Major League Baseball park, and they record data on every pitch thrown in every game. Using R and the PitchRX package, it's possible to scrape that data set, and the result of what you get back is a SQL-like R database of 10 tables. The tables and their relationship to each other are displayed on the right-hand side. For this project, I scraped the seasons 2008 through 2016, which left me with a resulting data set of about 6.8 million observations of 81 attributes. Now, fortunately, there's very little missing data in here and no extreme outliers, all of which is probably the result of the fact that the data is all captured automatically. There were a few cases of missing data, but in those cases where it did occur, it appeared that the system just failed to capture a pitch entirely because there was no data at all for those observations, and so they were simply omitted. While the data set itself is really great, high fidelity data, the measure of a pitcher really isn't so much about how he does on single individual pitches, but really is more about how he does over time and his consistency. So rather than using the raw data in its form, what I've done is I've taken the data set and I've derived features of aggregate data and assembled those into pitcher profile vectors, which are designed to characterize a pitcher based on what type of pitch does he throw, how many different pitches does he throw, where in the strike zone does he like to work at, what's the range of his fastball velocity, how much break do his breaking balls have, and that kind of information. The total vector is displayed on this screen. This diagram shows the overall flow of the analytics strategy. Moving from left to right, the raw data is ingested from the PitchFX database and combined with a small amount of career data from baseballreference.com, which is used to identify the first and last year of a pitcher's career, the game started, and most importantly, it's used to label the pitcher profile vectors for the classifier, indicating whether or not a particular season was that pitcher's last productive season or not. The data from the two sources is aggregated and used to derive the performance vectors. Unlabeled version of the profile vectors are fed to a k-means clustering algorithm, which is there primarily to validate that the profile vectors are accurately characterizing the pitchers and seeing whether or not similar pitchers will cluster together. Then labeled version of the vectors are split into a training and test data set and fed into an SVM classifier. The support vector machine was chosen specifically because, one, it's computationally efficient and because it handles high dimensionality data well. I do think, though, that it's important to emphasize here that I'm really not expecting to get a high degree of accuracy out of this classifier, given the large number of additional factors that feature into a player's career that are not included here, things like health and off-field issues. I just don't think that it's reasonable to expect that you're going to get really high levels of accuracy. And really where I see this analytic fitting at would be more as one stage of an overall pipeline of analysis, in which you might use this as the first stage to figure out which pictures you really want to look at very carefully later, where you could look at more specific things to that particular pitcher and start looking at time series analysis on how his performance has done over time, over recent years, and that kind of thing. Descriptive analytics are commonly used to create hypotheses, which you'll later test with your models. And in this particular case, the descriptive analytics have shown a couple of things that are really some age-old adages that all baseball players know. Included amongst which is that if you want to be a successful pitcher, you need to be able to throw strikes, and you have to be able to vary your speed and location with your pitches, which is really what these two charts are all about. The quad on the left-hand side is about pitch velocity by type. The box and whisker plots show the velocity range for different types of pitches, with successful pitchers on the left-hand side, targets equal 0, and unsuccessful pitchers on the right-hand side, target equal 1. And then the overlay density plots on the top show the difference in velocity between a pitcher's fastball and off-speed pitches. And what you can see is that the successful pitchers have a wider range between there. So they're doing a better job of varying their velocity in the different types of pitches. In the quad, also in the bottom right-hand corner, you can see that the box and whisker plots of different pitch types for unsuccessful pitchers tend to overlap. And so all pitches come in kind of looking at the same velocity, which is generally in the batter's favor. On the right-hand side are heat maps that show pitch location relative to the strike zone. It's a little bit hard to see in this small image, but there's a small dashed square in the center of both images that show where the strike zone is at. In both of these cases, the samples have been normalized so that both heat maps include the exact same number of pitches. And what you can see is that the successful pitchers on the left-hand side are throwing more strikes into the strike, are throwing more pitches into the strike zone, and that they vary the location so that they're using the entire strike zone. The unsuccessful pitchers on the right, on the other hand, are throwing fewer pitches into the strike zone, and when they do, their pitches tend to be like right in the center of the strike zone, which is a place where they get hit hard and often. As I mentioned before, the k-means clustering is being used really to see whether or not the profile vectors are going to do a good job of characterizing pitchers by type, and that's what I am seeing in the initial tests with the clustering. As we look at this chart, in the upper right-hand corner is a cluster of pitchers that are all right-handed, four-seam fastball, changeup pitchers. In the lower right-hand corner, those guys are all left-handed, cut fastball, curveball pitchers. The lower left-hand corner are all right-handed, sinker slider pitchers. And the one cluster that has one guy by himself is the one knuckleball pitcher that was included in the data set. The other clusters have got different combinations of things, but they are clustering similarly in relative baseball terms. In the next couple of weeks, I'll be using recursive feature elimination to try and reduce the dimensionality of the data a little bit, and then train and testing the classification model using the support vector machine initially, although I may use a random forest as well for some comparison. And then, time permitting, I may do some iteration on the performance characteristics and see whether or not other features within the vectors would do a better job. obviously, building on the work of lots of other people who have made some great contributions in this area, and it would only be appropriate to thank them. And at this point in time, I'd be happy to take any questions.
Was the Moneyball approach just in batting and on base, or did they also do pitching statistics? Was there stuff out there already to what to look for, or is this all fresh?
So there is some information out there. Some of this stuff has been done before. Heat maps have been used extensively, quite a bit. The Moneyball approach it initially started off with batting, although it has expanded to pretty much every aspect of the game now. Major League Baseball has a new system that just came online last year, also called StatCast, which includes some extra features that I think in time will help improve things quite a bit, because it includes actual measured spin rate and velocity and trajectory of balls as they leave the bat. But this is only the second season of that data being available, so there just wasn't enough of it to where I felt like that could be used this time.
Anybody have any other questions? Very nice work.
Yeah, who's next?
Actually, I had a question for Greg.
Oh, go ahead.
Greg, it was really funny. I sat on the plane today with a guy that works for Major League Baseball in their statistical department. But you brought the data from, I think you said 2008 to when?
2016.
So how have the attributes changed over the years, or how their measurements have changed that may have affected some of your analysis?
So that's a great question, because they are constantly, retuning their equipment, trying to make it better and better. And in one of the places where that's really significant is on the pitch, in determining the pitch type, right? How do you decide whether or not something was a curveball or a slider? And Major League Baseball actually uses a neural network classifier to make that determination. It's every year it gets a little bit better than it was the year before. There's heated debate among the sabermetrics guys about whether or not you should, to what extent you want to use that data, because it's not perfect. But for me, it really came down to is what's the better option, because it would be less than ideal to ignore pitch type and treat fastballs and curveballs as though they were the same pitches. And so right now, the classifier that they use is the best available data.
Cool, thanks.
Mm-hmm.
All right. Who is next?
Abigail's next.
Okay, I want to remind people it's 6:52. We've got till about 7:45, and then I have to kick you out so I can do a different WebEx. Abigail, let me see. So try to be succinct. All right, Abigail, you should be able to show your screen. Wait a minute, I dragged it to the wrong person. Now you should be able to show your screen. Go up there again.
Are you able to see my screen?
Yeah, yes, we are.
Okay. So I designed my project around a fictitious hospital that's concerned with increasing patient care. And the data I chose to analyze for this project was breast cancer data on benign and malignant tumors. So for my hospital, they recently had a survey done that revealed that they have low patient satisfaction and a high rate of initial misdiagnosis. So the hospital currently collects patient data, but they just store it and they don't implement any sort of data analytics. So in order to improve overall patient care and restore the hospital's reputation, an analytics team was established to develop models using sample data to predict patient diagnosis and present the findings to upper management in an effort to prove the benefits of analytics and how it can improve their survey scores. So for my sample data, it came from the UCI machine learning repository. It was originally collected by Dr. William Wolberg at the University of Wisconsin Hospitals from his breast cancer patients from January 1989 through November 1991. The data contained characteristics of the breast tumors of patients and an ultimate label corresponding to whether they were eventually diagnosed with either a cancerous or benign tumor. The data contained 699 records with 11 variables. Within RStudio, I loaded the data to explore it. All variables were stored as integer types initially, as can be seen in Figure 1. And then this would eventually need to be changed during data preparation, as the class variable should be categorical information and stored as a factor type. So here is a table showing the definitions of all of my variables. The ID provides a unique identifier for each record, and the other variables describe the tumor tissue cell differences. So cancer cells typically behave very erratically, and their cells will vary in shape and size. They have other key variances. They don't have marginal adhesion, which means they don't stick together, and their nuclei vary in structure from normal cell nuclei, such as not having cytoplasm. Mitosis, which is the process through which cells divide, is also measured. This is basically the mechanism that tells a cell to replicate, or it's the way in which cells do replicate. And in cancer, the mechanism that tells a cell to stop replicating is turned off, and they divide infinitely. So this is kind of the key characteristic of cancer. Overall, the variables just measure the differences between like healthy mitosis and mitosis set to overdrive. So here are some of the ways I explored the data. The pie chart shows that the majority of records were for benign tumors, which accounted for 458 entries. The remaining 241 records were for malignant breast tumors. The aggregate function was also used within R, and it summarized the data by median for each class. So overall, benign tumors were associated with lower ranked values, corresponding to things like a more uniform shape and size, normal nuclei, smooth texture, and normal mitosis, which is what we would expect. Malignant cells were more asymmetric in shape and size, formed thicker layers, had a rough texture, but they also strangely showed normal mitosis. As I said previously, it's been proven through multiple research studies that mitosis is kind of the way cells become cancerous. So it's very unlikely that the cancer cells would exhibit normal mitosis. And because of these findings, and the fact that I don't know exactly how the data was collected, I chose to remove the mitosis variable because I was afraid it could skew my analysis. There's no way to really know for sure whether the mitosis findings were correct or whether they were, or whether they were measured incorrectly. So the safest course of action, I thought, was to remove the variable altogether. This slide basically summarizes all of my data preparation. So there were 16 records that contained missing values for the bare nuclei variable. And because cancer behaves so erratically, the records with missing values were removed entirely instead of inputting averages. There was also 8 duplicate entries that were removed from the data set, and the unnecessary variables of ID and mitosis were then removed, along with the class variable being converted to a factor type. Outliers were also found within multiple variables, but I decided to keep them in for my analysis. Since cancer can produce such extreme abnormalities, I thought that these outliers were a good reflection of the real world. So the ultimate issue of the hospital is that they have a high degree of incorrect diagnosis given, which impacts their patient care and satisfaction. So because of this, I'm going to be doing both prediction and descriptive models. The prediction models will provide a recommendation on how a tumor should be labeled. This can verify a doctor's diagnosis or make them re-verify their findings if they don't agree with the recommendation the model provides. The prediction could also be obtained more quickly and could provide a good indication to how a doctor should treat a patient even before any other results come back, like blood tests or x-rays. The descriptive statistics and model will then provide further insight into the characteristics of the patient base overall. It's the hope that that will provide the doctors with the ability to give personalized care and truly understand the risk factors associated with cancerous tumors. So I'm going to be creating a normal decision tree within Enterprise Miner, along with a gradient boosting decision tree and a random forest model. And then since the data contains a binary target variable, I'm going to do a logistical regression model within Enterprise Miner as well for comparison. The final prediction model will then be compared against a decision tree that's going to be created within IBM's Watson. And then the ultimate goal of my analysis is to create at least one model that can predict whether a tumor is cancerous or not with 80% accuracy. Creating these multiple variations of models allows for a broader range of comparison for analysis and the ultimate creation of a more accurate prediction model. I'm then going to use RStudio to do k-means clustering to group the patients based on similar characteristics and results. These clusters, along with the diagnosis verification the prediction models provide, should help to improve patient care and satisfaction overall and help doctors be more confident in the care they provide to patients. The overall lessons I learned so far include really seeing the importance of exploring the data prior to preparation. Through the visualizations and analysis, I was able to find that there were duplicate IDs, but not all of the duplicate ID records were true duplicates. I had to use the unique command within R to explore them further. So I found 55 duplicated IDs, but only 8 of them had duplicate values for every variable. So I think a lot of the data was collected by hand, so it's possible someone just didn't keep track of the IDs and duplicated some. If I hadn't really dived into the data, I would have just removed 55 records off the bat, which really would have cut into my data set. I think it's also important to have a good understanding of the variables you're working with. It helped me to key into the fact that that mitosis variable wasn't behaving as it should, and I saw it as a potential risk to the analysis. So instead of messing with the values in any way, I just chose to remove it entirely. I think that's a good rule of thumb when you aren't sure where the data you're using is coming from. If I hadn't done that, I really could have skewed my analysis and messed up my entire model. So barring any questions, that's all I have for now.
What's the time frame this data is from?
I have to look back at my slide. It's from the late 80s to the early 90s. Okay. Yes, 89 to 91.
Okay. Thank you. Mm-hmm. Any questions for Abigail?
All right, who's next in the lineup?
Alexander.
Let me see if I can get the ball down to Alexander. Where is he? Oh, I see. Okay, hold on. Okay, Alexander, you should be good to go.
Okay, can you hear me?
Yes.
Okay, perfect.
Up there
okay,
to share,
so
and you got to go to share to get your screen.
Oh, do I? I'm sorry. Let me hit that.
Up at the top there where it says share, and then the pull down. You should
share my screen.
There you go. Now we see it.
Perfect. So this is my presentation. This is a look into several decades of fuel economy data. I'll be pretty brief on all these since we just have 5 minutes and I have a lot of aspects to get to, so it'll just be a quick overview and we can get more specific in the discussion. But in terms of the project scope, obviously fuel is a ridiculously tremendously important commodity in today's age. Wars are waged over it. It costs God knows how much money. And it's kind of not going anywhere. So it's obviously very important. And the economy of cars regarding fuel is obviously echoed in that same vein. So my project is basically tracking the fuel economy of cars. We can track several decades worth of fuel economy. And not only can we predict it accurately with our current standards that we have for cars, but since we're tracking over several years, we can basically do a sort of a time analysis and see how it's going to change in the future. But being a little more specific here, my data, the original data, had a little over 37,000 records. It had 83 variables. It comes from a place called CAPSART, K-P-S-A-R-T, that stands for King Abdullah Petroleum Studies and Research. I have honestly never used this up until this project, but it has a lot of really cool stuff, basically just about petroleum. So if you ever need a data set that's pretty useful, this would be the one. It has a lot of independent variables, such as number of cylinders, make, model, year, manufacturer, just basically anything you can think of with your car, any aspect of it. That's going to pretty much be in this data set. And it also has dependent variables, which are basically miles per gallon, but I'm going to get to that in just a minute. So this is one example of how much data was in this original data set. There are so many variables. We really needed to cut these down. This is about a third of what I originally had. So this is just kind of to show that the data preprocessing thing was a little more extensive in terms of choosing which variables that we need. But after a little bit of work, we have a revised data set of just those variables. This was basically done, this data set, once I got into it, it had a lot of values of 0. And I found out that basically they were using 0 as a missing observation. So, for example, they segregated electric cars and non-electric cars. So if you had a variable that's something along the lines of electricity kilowatt per hour, they would just put 0 for all standard cars. And if your car was an 84, that makes no sense to measure this variable if it can't feasibly have a value. So a lot of variables I could just take out that were related to electric cars, a lot that were related to fuel type 2, which is basically anything that's non-gasoline. Basically anything where we're talking this only has existed for the last few years, I could cut those variables, and that took them pretty low. And then beyond that, it was just a matter of picking and choosing what kind of looked important. And then the two variables that we have in the red there, miles per gallon, this is a linear variable. And then I also created a binary variable of this, which is basically based on the mean of the miles per gallon. So say the miles per gallon average turns out to be 21. Anybody below 21 will have a value of 0, and anybody above will have a value of 1. This is in order to basically do more models. As you can see at the bottom, in terms of a linear value variable, I'm going to do linear regression and support vector machine regression. And for the binary, I'm going to do logistic regression, decision trees, random forest, gradient boosting, and ensemble modeling, hopefully on top of that. But in terms of the tools that I'm using, mainly Excel and SQL for the data manipulation. I'm using Tableau and Enterprise Miner for the visualizations. For Tableau, it'll be kind of the pre-processing stuff, and Enterprise Miner will be the post stuff, such as sensitivity and specificity and collinearity of variables and that type of thing. And I already discussed the models that I'll be using. Again, this is just basically to hopefully predict fuel economy of cars in a little more specific way and kind of see where we're trending, so I can see in 10 years if I know the values of the variables that I'll have. I can already predict what the fuel economy is going to be in order to better predict manufacturers creating those cars. Just real briefly, lesson learned so far. It's good to start early, obviously. You want to find a good data set, one that you can do analysis that you are comfortable with. There's a ton of resources out there, so, it's not hard to find those. Using tools and analytics types that you're confident with is key. I have very little R experience, so I thought it would be ridiculous for me to choose R for this course project, so I learned something I know, like fast. And then utilizing class discussion and any other resources is tremendously important for this course, since there are a lot of great resources out there. But that's all I had so far. I would be happy to take any questions.
What was the data set or the location of the data set where you found a lot of good items?
Sure. This one specifically, I wouldn't say is a lot of good ones. It's called CapSarc. This basically just has a ton of data based on petroleum. So anything fuel, this is where you want to go.
Okay.
Any other questions?
Okay. Who would be on the next on the agenda, John?
Lauren.
All right, let me get it down to Lauren. Let's see, I got to figure out how to drag this thing down to Lauren. Hold on a second.
I think I got it. No.
You do now. Lauren, you should have control now. And I think I see your screen and I hear you. Go ahead.
Awesome. Hi, everybody. So I am doing my project on commercial inventory on television commercials. It's actually where I work. I work for Comcast Spotlight. We are the advertising sales division of Comcast, NBC, Universal. So I have to have my disclaimer. This analysis may only be used in this classroom and not referenced or utilized in any other setting, because I am using proprietary data. I actually have a meeting with our legal team tomorrow as well. So continuing to make sure that it all stays confidential and, you know, as we do in the corporate world. But I'm very happy that I was able to use it from work. So this presentation, I'll go through it pretty quickly. But try to give you all a good snapshot of what we do and what the problem is, and then go through some of the data sets I was able to access, the techniques that I'm using in the analysis, and the lessons, and obviously the references at the end. So as far as the problem and the scope, we have commercial inventory both on air television and online digitally. And we have it across the entire country, but also within individual zones in geographical locations. So right now I sit in our Seattle office, and so we have the Northwest, which has 5 markets, including Seattle. But then within Seattle, there's 10 to 15 geographic zones that we are able to put local commercials on in our across 50 networks on cable television. So we have this commercial inventory with various selling strategies throughout the company, throughout each local sales office, and then we have different pricing strategies as well. And we can sell the zones across the entire market, which would be the interconnect, but also individually as well. So we have different kinds of allocation that we can do. So there's a lot of decisions being made there in terms of how much does one commercial spot cost in one zone on one network during one day part. So saying, you know, an 8 p.m. to a 9 p.m. commercial spot might cost different than a 12 noon to a 1 p.m. Or we might have a broad rotator that, you know, runs between 6 a.m. and 12 midnight. So there's different selling strategies as far as how many hours they're putting in an order, and then there's different pricing strategies as we kind of compress within the zones and the networks. So there's a lot of data going on here, and there's a lot of ways that we can be smarter with our data and with our pricing strategies. So my role actually in the company is I'm a revenue opportunity manager, and so I oversee our pricing and planning team for the Northwest region. So this is very relevant to my job. And we are you know, in the midst of trying to figure out how we can best utilize our data and think about the techniques that are used throughout the company. And so this is very, very relevant. So as far as the data sets that I used, I'm really looking at data from starting Q2 of 2016, so April of 2016, all the way through Q1 of 2017, which goes through March. I was looking at sellout. So these are various data sets that I was using. So sellout data, looking at our capacity in the inventory in the past, which is why I only went through Q1 of 2017, and seeing where our sellout is in our zones across our networks, across the different day parts. The ordered spots, so that's 11 variables, which looks at what are the actual orders that went in and how were they ordered. And then we also have drop spots. So with our commercial inventory, spots can drop for various issues. One of those big issues that we can actually affect on the front end is the selling strategies. So sometimes we only have one local break in a network in an hour, and they will, and some of the sales representatives will order more than one commercial in that hour. So that would be an oversell situation where those spots will be dropped and we'll lose that revenue. So looking at our drop spots report over that period of time, we have impressions. So when we're thinking about the value of a spot, it's how many people are actually watching television at that time. So one thing that we look at in terms of value is cost per impressions, which would be actually cost per 1,000 impressions is how we look at it. So to have the impressions across networks, across zones, and across the whole interconnect, and seeing what we are charging per spot as an average unit rate, and then where we want to be to make the revenue that we're looking at. And as I stated in the beginning, because this is all confidential, I am putting keys in for advertisers, for our zones, for our day parts, to make sure that everything is kind of coded and not able to be worked out in the back end, to keep it all confidential. So as far as techniques go, a lot of descriptive analytics. We have a lot of data here that we're working with in terms of exploration. What are the trends? Is there correlation between a sales representative selling a certain day part, or selling out or getting drop spots, or an advertiser that's buying a certain way? So one thing that I didn't mention in terms of selling strategies is that we have priority codes. So if an advertiser puts in an order, an annual order for the entire year, they have a different priority code than somebody that just bought it that month. So we're able to kind of look at the inventory with levels of priority on what's supposed to run and what is not. We have time periods, networks, zones, as I stated. So kind of looking at exploring that data in Tableau with priority codes and time periods. So for this example, time periods across Q1, Q2, Q3, Q4, and across our priority codes, and what is the number that we have that of orders actually going in, and what is the revenue attached to that order. So we can see how different priority codes have different revenue values assigned with them, even though there may be more or less records assigned to that. Another look at the data is what I was doing is our networks and our day parts. So length of day part, this can be anywhere from 1 hour, and this was an average length of day part. So a lot of these are 1 hour increments, or in the most years 2 hour increments. But we can also get down to like a half hour, and if we're looking at impressions, even a quarter hour. So depending on the data set that we're pulling, we can really see how many records are ordered a certain way and how we can really affect those orders. And if one network, like let's say Travel Channel, is ordered a certain way as opposed to something like HGTV ordered a different way. And then we look across the zones and seeing how much revenue is put into each zone. So should we have different strategies for those more popular zones, or what is our pricing strategy for that? And so a lot of exploration here in terms of the data that we have. And then the different techniques in terms of the analysis and modeling that we're going into. So clustering, a lot of different ways to cluster, just like I was talking about with orders, network, zones. A few things that I'm looking at in terms of predictive modeling with decision trees is sellout. So one of our goals is to have at least 85% sellout. But with that sellout, we want to make our revenue goals as well. So where is that that pricing strategy in terms of what will our pricing be based on cost per 1,000 impression or cost per spot or average unit rate to get that sell out at 85% or higher. And then also the predicting of the drop spots, so for oversell or different kinds of exceptions that would cause a drop spot. And then lastly, the artificial neural networks, looking at pricing based on our impression and sellout so that we can find our areas of opportunity to classify, where we're looking at which zones and which networks to effectively price a certain way and use a different pricing strategy based on what the different variable calls for. So far, lessons, confidentiality is a huge one. It's, making sure everything's coded in a way that makes sense and is able to keep our proprietary data internal. It was funny when we were talking with Greg with MLB data. They had it published years ago, and now that it's public, they can't privatize that and then sell it. But with the data that we have in such a big company, we are holding onto that data and we're not publishing it and we're keeping it internally. So it's a big deal. And then the challenges of defining the correct evaluation of pricing and pricing strategies. And as far as planning, so understanding our sales strategies, because I'm in it, I know how we're selling. I've been with the company for coming up on 4 years. I understand how we're looking at it and how our different sales strategies are across the market and the data that we have and that connection to the data sets and tools. And then lastly, I was looking at different inventory and pricing models that have been cited previously in research and trying to apply different types of techniques to the way that we're looking at it here. Any questions?
So have you shown data to your teams or your executives at this point?
Not at this point, no.
Okay. Is that after the lawyers? Or?
Yes. I showed a plan to my manager and above, and we're passing it up the chain. So the plan they're saying looks good, and different concerns that they have, and as we're kind of massaging it to make it work internally.
Okay.
All righty.
I think that's it.
Oh, okay. Well, that's, I can say from my perspective, those were very interesting. So I think a great idea that you had, John. I think looks like something we'd want to continue going into the future. And, of course, you got another session on Thursday for some others, I guess.
Yep.
Was everyone here tonight in your class, or were there any people who might be coming into the course next time?
I think it was mostly my class, but I'm going to post the recording to make it available to you and others to show your classes.
Sure. I assume what Lauren's shown so far wouldn't be a problem to show to my class, again, with the same caveat.
It shouldn't be. We should be okay.
Great. Well, I'll go ahead and stop the recorder, and I'll send you the link, and you can post it in your class, and then I'll post it in my class. And And I think it was very interesting from my perspective. Thanks, everybody.
Thank you.
Thank you.
Thank you. Thank you.